Okay, so the video stops. Let's continue that. The theorem 8 says the sequence of this integral, it's a number. A sequence of number will converge to the integral of f of z. So a sequence converge to some value. So that's a theorem 8. And it looks very complex. Let's write it in one line. So see here, the statement says the sequence will converge. So we're talking about the limit. The limit of this sequence is equal to the integral fz dz integral. Okay, I put integral here. Fz, we know fz is the limit of fn, so we write limit fn of dz. So that's the one-line statement about the theorem 8. So the theorem 8 claims if you have uniform convergence, you have integral, then this limit operation, integral operation, they can commute. Okay? So the limit operation, integral operation, they can commute. It doesn't matter which order you use. So that's what this theorem 8 means. Okay. Let's see how do we prove it. First of all, f is continuous based on lemma 3. So this integral f of z dz along gamma exists. Okay, so that's the important thing. And also for the gamma has length L. We assume gamma is a contour. It definitely has a length. We talk about a nice contour. Gamma has length L, and the uniform convergence. Then for any epsilon, there is a capital N such that for any n greater than capital N, fn of z minus f of z is less than certain copy of a certain multiple of epsilon. Let's leave a blank here. At this moment, because we didn't do we don't do the future computation, we don't know what is the adjust coefficient. Let's leave this coefficient here. Okay, for every z, for all z on gamma, then this is a preparation. Basically, this is all the information we know. Then let's compute. We want to check the convergence of two numbers, of a sequence with a number. So let's check the difference. The difference, first of all, write them in one integral. And second, apply the inequality. You move this opposite value into the integral, right? That's a standard, typical trick. And if we can estimate this, control this, then it change it to be a constant. Make this a constant. then you can move this constant forward, then you multiply the stuff by the length of gamma. So you have the length of gamma and times this constant. You want this constant related to epsilon. So times this one, check here. We want 1 over L. The reason we want 1 over L because here you have L. We put 1 over L, we can cancel it with L. Okay? So if for every point on gamma, this difference is less than 1 over L, L is fixed, 1 over L times epsilon, then this place you are going to put 1 over L epsilon here. It's a maximum value, it's upper bound, and times L. So this is epsilon, right? Less than, no equal. Here we use strict less than. Okay, so that is the strategy to determine this coefficient. And this just means the convergence. So we finish. Finish it. So once you have uniform convergence limit, then it doesn't matter you do the integral first, limit second, or limit first, integral second. You will have the same answer by the theorem 8. Okay. So this is an abstract discussion because it's only related to the continuous function. Now let's apply this to our analytic function. So Fn be a sequence of analytic function. Analytic function in a simply connected domain D and converging uniformly to F in D. So you have a sequence of an analytic function and you have its uniform converging limit. Okay. At this moment we only claim is the limit. Then F is analytic in D. So you see here the limit, the uniform limit of analytic functions is analytic. So that's a one sentence statement. Uniform limit of analytic function is analytic. So analyticity is preserved by the uniform, very important, uniform convergence. It is preserved by the uniform convergence. Well, how do we show it is differentiable? We actually don't directly prove F is differentiable. We prove the Morera theorem. Okay, so what is the Morera theorem? So given any triangular path, right? Given any loop, so first of all, for any loop, contained in D, the Morera theorem says, not Morera theorem. At this moment, Fn is continuous. Fn is continuous. Then the integral of Fn along and the loop gamma converges to the integral of f along gamma by theorem 8. Okay, so this is only continuity. It's only continuity. And f is analytic. Fn is analytic. And region D is simply connected. Then this gamma can be contracted to 0. In other words, the integral of Fn along gamma is always 0, the Cauchy theorem. Right? Integral of Fn along gamma is always 0. And this implies the integral of f along gamma is always 0, because that's a limit of 0 is 0. So if for every loop the integral of f along gamma is always 0 by Moreira theorem, f is analytic. Okay, so we do not directly compute the derivative. We apply the Moreira theorem by the integration. Okay, so now we have everything we want to study the power series. The power series, you see, it is a sum of power functions. Each of them is analytic, and you can consider the partial sum, right? You can consider the partial sum is always an analytic function. So the power series is a limit of a sequence of analytic functions. And if you have the convergence, then you can pass it to the limit. Okay, so that's a theorem 10. Theorem 10 is the following: a power series sums to a function that is analytic at every point inside its circle of convergence. Why we have this theorem 10? So first of all, you have a circles. Remember what is a circles of convergence. Circles of convergence is like this. So inside it converges. Outside it diverges. So here's converge. Divergent. Along the circle, some point converge, some point diverge. We don't know. And another important property is that for any subdisk, inside the subdisk is uniformly convergence. Inside the open disk, it is just convergence. Okay, so inside this subdisk, it's uniformly convergence. So if you have a point z inside a certain subdisk, then the function f, power series, represent the function f is the limit of analytic function, uniform limit of analytic function. So function f is going to be analytic at the point z. So inside any closed subdisk, power series is uniformly convergence. just only inside the open disk it's not uniform. But with this uniform convergence by theorem 9, the power series is analytic. At Z, right? Theorem 9 just say if you have a uniform convergence and of a sequence of analytic functions. Why it is analytic? Because it's here the sequence of Fn is the sequence of partial sums Fn of Z is sigma k from 0 to n ak z minus z0 to k's power. And this is a polynomial. Of course it is analytic. They are polynomials. And analytic. Okay, so that's the reason we can apply all the theorems we have. Okay, so we do have that if you have a circle of convergence, then the power series will be analytic inside. Outside it diverges, so we don't discuss analyticity. On the circle, it may or may not converge, so we don't discuss analyticity. Okay, so we still don't know how to find the radius of convergence or the circle of convergence. That's fine. For some special case, we can discuss it. And once we have a power series representing an analytic function, we can relate it to the Taylor series, right? So Taylor series, the coefficient is J's derivative evaluated at the center over J factorial. Here is a similar thing. The theorem 11, if sigma J from 0 to infinity aj z minus z0 J's power converges to f of z in some neighborhood of z0. Actually, this just means it's not just converge at one point. The series does not only converge at z0. Does not only converge. It converges in a small region. It contains an other point. Not just z0. If we have such a thing, then we can consider this power series as a Taylor series of a function. So what does it mean considered as a Taylor series? So the aj is J's factorial of this power series function evaluated z0 over J factorial. J's derivative, my bad, J's derivative of f evaluated at z0 over J factorial. Okay, so this is our case. And consequently, this series is the Taylor expansion, Taylor series of f. Okay. It's a Taylor series of f. So for the analytic function, you can develop it. It's a Taylor series. And for the power series, you can construct an analytic function, and eventually this original power series is just a Taylor series of that analytic function. So they are one-to-one corresponding to each other. Okay. So let's check. Let's check. How do we show this one? So first, in order to apply it, we need a circle. So let C be a positively oriented. Positively oriented just means counterclockwise. Circle centered, positively oriented circle centered at Z0, and lying inside the convergence circle, the circle of convergence. So circle of convergence, Z0. And you choose a circle this way. This is the picture. Okay, so we already know that by the theorem 10, theorem 9, we know that f of z is analytic inside the circle of a convergence. Analytic inside the circle of convergence, then we do have the Cauchy integral formula for the nth derivative. This is the Cauchy integral formula for the nth derivative. Cauchy integral formula. Okay, and then what's next? Remember, we have term by term integral. We have term by term integral that depend on the theorem 8. When you have a uniform convergence, you can pass it to the limit. So we are going to integrate term by term. And you see, f theta is sigma aj and z minus z0 to j's theta minus z0. And then we divide it by theta minus z0 to power n plus 1. And then we're going to do integral, and we'll put integral here. And remember that here we should put it outside, but because this is uniform convergence, we can put it inside. The limit of integral is the integral of the limit. Remember, that is the theorem 8. The limit of the integral is the integral of the limit. The integral of the limit is the limit of the integral. So you integrate each term. integrate each term. And for this type of integral, we know that it's 0 if j is not equal to n. If j is equal to, you see here, when j is equal to n, when j is equal to n, you cancel theta minus z0 to nth power, you will get 1 over theta minus z0. 1 over theta minus z0 is 2 pi I. So this integral, this series, the sum of the integrals, actually only contain one non-zero term. It only contains one non-zero term, right? Okay, so what we get? We get this integral equal 2 pi I times aj. So integral is 2 pi I times aj. You plug in here this one, you put it here. You get nth derivative f of z0 is equal to n factorial 2 pi I, and then this 2 pi I times aj. So cancel 2 pi I, you will get aj is an. A sub n, my bad. A sub n. An is nth derivative over n factorial. Okay? So this is the proof. The power series represents the Taylor series of the limit. Okay, so now let's see some theorem example. Let's see some example. The first example, we find a function f that is analytic and satisfies the differential equation df dz of z is equal to 3I times f of z in the neighborhood of z equal to 0 with f of 0 is equal to 1. Okay, so that's the problem. So we don't want to, of course we can solve it. Remember that if you have f prime is a number like k times f, you get like the y prime is ky. This is actually the exponential growth formula, exponential change. So you get dy dx is ky, so 1 over y dy is k dx. So the integral of 1 over y dy is integral k dx. This is a natural log of y is kx plus c. So upper value of y is exponential kx plus c is a c prime e to kx, and the y is you put plus or minus, you get this solution. So this is the way to find the exponential growth or the exponential decay. And now we don't want to go through this part. We want to apply the power series. Assume we have the power series. It's in the neighborhood of zero. So you have a this simple power series, a n z to n. Now let's check what is the derivative relation. F prime of z. F prime of z becomes a1, a2, a1, no, let me check. It's a 2a2 z and 3a3 z squared, right? Power series. Let's check here. A0, a1z, a2z squared, a3z cubed. So if you try it, it's a 4a4z cubed. Go on. And then you get this equation. Equation says 3i times this line is equal to the next line. So you get 3i a0 is equal to a1. 3i a1 is equal to, 3i a1 is equal to 2a2. And 3i a2 is a 3a3. Okay, so you have 3i a3 is 4a4, and so on. And you have a condition, f0 is 1. f0 is 1 means a0 is equal to 1. a0 is equal to 1, you get a1 is equal to 3i. Check here, a1 and 3i. a1 and 3i, you get a2 is 3i squared over 2, right? 3i times 3i, 3i squared divided by 2. a3 is the 3i cubed divided by 2 and divided by 3. It's actually 3i cubed 3 factorial. And a4, if you do it, you will see it is a 3i to 4 factorial. So follow this pattern, you will see that an is 3i to n factorial. So what is f? F of z becomes sigma 3i to n factorial z to n from 0 to infinity. And combine 3i with the z, you get 3iz to nth power over n factorial n from 0 to infinity. This is exactly the exponential e to 3iz. E to 3iz. Okay, so actually it follows the same stuff. Follow the same stuff. Here k is the 3i. So here is a 3ix, 3iz, the same thing. And a is the initial value. A is equal to 1. Okay. Assume you have the power series representation, Taylor series representation. Assume you can simplify the final Taylor series, power series. You actually can recover the classical result by this power series process. But the classical result depend on some technique, integration technique. Power series basically only depend on this comparison of coefficients if it's not too bad. Okay. And this Taylor series method can be used to some general differential equation. So we have the following: for the nth order linear homogeneous nth order linear homogeneous differential equation. Okay, so that's a name. Now let's see what is the meaning. So nth derivative Pn minus 1 over z, n minus 1's derivative, blah blah blah, and P1 over z f prime and P0 over z equal to 0. So linear means for each derivative plus original function, my bad, original function. So linear means for each derivative and original function, it's just power 1. So that's a linear. Homogeneous means here is 0 and there's no, and the constant term is 0. The constant term is 0, homogeneous. Differential means you have derivative. For this equation, the with the condition, with the condition f of z0 equal to a0, f prime of z0 equal to a1, and fn minus 1 of z0 is equal to an minus 1. You have a nth order. You need n initial condition. For this differential equation, there is at some point z0. At some point z0, there is a solution, analytic solution. In order to get analytic solution, you have to assume all the coefficients analytic. The analytic inside the disk centered at z0. So there's many conditions. Then there is one and only one analytic function. Fz satisfying all conditions. Satisfy all conditions. So this is about the existence and uniqueness of a solution for the nth order linear homogeneous differential equations. And how do you do that? You just represent, assume you have analytic function. It has a power series representation, the Taylor representation, and you satisfy this equation. You solve this homogeneous linear equation. You solve this homogeneous linear equation, you will get the answer. The uniqueness, that's existence. The uniqueness comes from if you have the analytic function, then it must satisfy the same process, and you get the same solution. Okay, so that is the application or the usage of the power series. And another thing, another example, and we stop. Another example says, let G be a complex valued continuous function of a real variable on 0, 2. So its value is complex. Its domain is real. It's a real variable. And for each complex number z, define f of z equal to the integral from 0 to 2 e to zt gt dt e to zt gt dt. Okay, so you integrate here. You integrate a complex valued function. Basically, you integrate the real part and imaginary part and add them together. Okay, and then we prove f of z is entire. Entire just means it's analytic for whatever z. And find its power series. Around the origin. Basically, we're looking for the Maclaurin series. Okay, so how do we do that? How do we do that? First, we know that this is an exponential function. Exponential function is analytic everywhere. It's entire. So exponential function has a power series representation. And it converges uniformly over whatever closed disk. Because its circle of convergence is a whole complex plan. Okay, so for whatever closed disk, it is always a ZT. It's always uniformly convergent. Okay, so if you fix Z, you can claim T, the relation about T, but here let's just put Z and T together. Okay, and then after this, we multiply this function pointwise by G of T. We multiply it pointwise by G of T, then it is also equal to sigma z t to k factorial and G of T. This is still convergence and uniform convergence because it's uniform convergence about this part. Here it's just coefficient. It does not change. And put T together. Put T together, it's like this. Okay, so if we fix here you see here this depend on the Z times T for arbitrary R. So if we fix Z for it's e to zt gt. This uniformly converges to e zt gt. Okay, so we fix Z, we only consider R. Of course, Z is not 0. Especially we make this R bigger. R is greater than 2. Two. R is greater than 2. R is greater than 2. So the 02 is contained in this domain. 02 is contained in the domain. Okay, then by theorem 8, the integral. We know that the integral of the integral of the limit is the limit of the integral. You just organize them and leave z to k isolated, and the rest of them you consider it as a coefficient. Okay, so this is the Maclaurin series, the Taylor series, or the power series. It converges for all z. Here you fix z, you have this. So it does not, the convergence depend on this t part. It does not depend on the z part. So it converges for all z. So f is entire. F is entire. And also we find the Maclaurin series for the for this entire function. We have this Maclaurin series. This is the Maclaurin series, or the Taylor series, power series representation. Okay, so here we finish the section 5.2. So in section 5.3, the section 5.3. In section 5.4, it gave us a discussion about the radius of convergence. Section 5.4 is the theory of a radius convergence. How do we define it in the right notation? We are going to skip it. We're going to skip this section. Next time is the last lecture. We are going to study the Lorentz series expansion. Possibly we will skip some proof and just give the idea. But you should read it. Read it. It's very important. If you continue this complex analysis study in the graduate course, we will literally prove this, but this moment we will not prove it. And in the graduate course, we will also study the Lorentz series. Okay, we'll stop here for today. Okay, thank you.